Okay. All right, good afternoon. It's 12:01. We will go ahead and start. I know that some of our audience have to cut across the campus to get here, so a few more people will be tripping in a few minutes. But I'll use that opportunity to introduce our speaker. My name is Zheng. I'm a professor and chair of the public health program. And we host this seminar series. Typically it's every other Monday, but every now and then we really want to get somebody here, and they can only do it on the alternate Mondays, and we try to accommodate that. So today is one of those days, and we've been trying to get Dr. Khai Zheng for a while, and we're lucky to have him. The seminar series is made possible because our faculty, students, staff, and colleagues across campus come to this series, and they nominate speakers for typically a year in advance. And today's speaker was introduced to us by a colleague who's also a member of the program in public health, Dr. Yunan Chen, by secondary appointment, but we really want her to have more interaction with public health students and faculty, and she teaches courses in health informatics that many of our students enroll in. So we've been trying to develop joint programs with informatics for some time. Health informatics is one of the really rapidly growing areas of public health and of informatics. And electronic medical records, I think it's inevitable. We have a unique opportunity to push the boundaries of knowledge and practice, given the Affordable Care Act and all the changes that are taking place in healthcare nationally and actually internationally. So we thank Dr. Chen for introducing us to the speaker today. We also thank the Office of Extension for always being there for us to reach a broader audience. We typically record these seminars, and they are available on the OpenCourseware website. So if you want to consult the talk at a later date, you can check that website, or you can send links to those who are not able to be here this morning. I am glad that Dr. Zheng made the trip. I think it was supposed to be sometime either next week or the week after, and we certainly managed to make it work. He's a very busy person. He's currently an associate professor of health management and policy in the School of Public Health, and associate professor of information in the School of Information at the University of Michigan. He's also affiliated with the University of Michigan School of Nursing, Michigan Institute for Clinical and Health Research, Medical School Department of Computational Medicine and Bioinformatics, as well as the Center for Entrepreneurship. So those affiliations alone can tell you how busy he must be. That's not enough. He co-directs the Biorepository and Biomedical Informatics Core of the University of Michigan Health System, and across the pond, the Peking University Health Science Center Joint Institute for Translational and Clinical Research. These responsibilities are certainly major, but he earned every aspect of the expertise that made him highly sought after. His Ph.D. is from Carnegie Mellon University, and he earned it by doing a dissertation on design, implementation, user acceptance, and evaluation of a clinical decision support system for evidence-based medical practice. This dissertation won the university's 2007 William Cooper Doctoral Dissertation Award in Management Science. He's a recipient of the 2011 American Medical Informatics Association's New Investigator Award that recognizes early informatics contributions and significant scholarly contributions on the basis of scientific merit and research excellence. Please join me to welcome Dr. Khai Zheng to UC Irvine and to the program in Public Health and the School of Informatics.
Thank you. Thank you for the introduction. Can you hear me fine? I'm wearing 2 microphones, which is unusual. I'm very glad to be here. My name is Khai Zheng, associate professor in both School of Public Health and School of Information at the University of Michigan. It's kind of a weird combination if you are not familiar with health informatics. But if you are, this is actually the perfect compilation. So what we do in health informatics is to provide technology support for population health management. And that's the joint mission between a public health school and an information school. So today I'm going to talk about collaborative search in electronic health records, which is about information retrieval from electronic health records for a lot of different objectives, for instance, research, clinical practice, and also regulatory audits. So I'll go into detail of the topic of the talk in a little bit. And I just want to say that I really love your campus. It's one of the most beautiful campuses I have ever been. And if you have been to Michigan, it's lovely as well, but not for 6 months of the year. It's just slow and very cold. All right. So before I dive into today's topic, I want to talk a little bit about my overall research background, so you get a sense about what I do, and also what I was doing or I am doing led to what I'm going to present today. So my primary interest and also the domain I trained in is human-computer interaction. So essentially, that's the domain where we study how technology is being used by human beings, and also how people becomes much more interactive and they talk and communicate with each other through technology. So within human-computer interaction, I'm particularly interested in 2 topics. One is workflow of the impact of health IT, and the other is user interface design. So I'll talk about the first one. The workflow impact of health IT is a significant issue right now. So many hospitals and physician offices are implementing electronic health records or other types of health IT applications. And one big negative consequence is the impact of the workflow. So the introduction of technology is totally changing how physicians, nurses, pharmacists, they interact with each other and also the patient in terms of their workflow. And I study very closely what that impact is and what does it mean. So this is one of the projects we're doing right now, sponsored by AHRQ, the Agency of Healthcare Research and Quality. So essentially, we use iPad as a tool to gather data of time and motion data about what physicians do or clinicians do at what point in time, for how long. And we also use RFID tags to track where people are in a hospital environment. We also use a lot of other trace information, such as electronic log files in a computer system, such as their email sent among clinicians. So we use a lot of information to kind of trace what they do. And then we try to construct a social temporal type of activities of physicians and nurses and so forth, how they travel, how they move around in a hospital, and how they interact with other people, both other medical professionals as well as patients. And what does it mean in terms of both floor plan as well as the location of technologies such as printers, such as computer terminals and so forth, and how that play into this whole story of how technology use may impact workflow of clinicians that then have an impact on both their work as well as patient outcomes. So we construct some kind of visualization demonstrating the workflow of clinicians. So in this particular study, we have observation before implementation of a system and then after implementation of the system. So we try to compare what is different in terms of workflow and caused by the introduction of Cos 19. As you can see that so one conclusion we have is this is before implementation of IT, this is after. So what's the difference if you just by visually, what kind of difference would you say comparing this graph and this graph?
The bottom is busier.
The bottom is busier. Yes, there are lots of color transitions. So meaning that a person, so each color represents a task, a clinical task. So before the system was implemented, they have time to do one thing for a long period. So before they switch to the other one. And bottom portion, so people they have to switch tasks frequently, which means more cognitive node and also more physical movements. So that's the kind of the conclusion you can even tell just from the visualization video. And similarly, we also calculate the transition frequency across different tasks and determine what are the before and after changes and what does the changes mean. So the next topic under human-computer interaction I studied is user interface design. So this particular system. What we did is we implemented some kind of software agent that would track how people navigate across different functions of the EHR. So this is an electronic health records system that captures a lot of different types of patient data. And there are so many different functions, and we actually don't know what might be the sequence a physician would use. So when they log into the system, what do they look at first? And then what do they look at after the first item? So if you know that sequence, it means a lot. It means that you can redesign the user interface to optimize the UI design with clinicians' mental model. So this is how they access data. And this is probably how also the visual elements on the screen should be arranged. So what we did is we capture those events, and when we calculate the transition probability across different functions. So essentially, if you are using A, what is the likelihood you're going to use function B? And so if we know that's almost 90%, then it probably makes sense to put the A and B next to each other on the user interface or create some kind of a hyperlink or shortcuts, sort of thing, to facilitate that kind of frequent transition. We also studied something called exit strategy, which is very interesting, so I really want to mention this. So essentially what we did is in a EHR system, you have to enter a lot of information data. So what about if you don't know what to do in terms of here? You try to enter a diagnosis, you try to enter code. What if you actually don't know the code, but you still want to send the patient out of the room in 15 minutes? You can't really spend an hour trying to figure out what to do with the system. So we provide an exit strategy. So this diagnosis is entered under a temporary code. So just meaning that we provided a lot of exit strategy like that in the EHR system and see how people would react to them. Are they going to abuse them so that they can speed up their work, or are they going to be used them in a much more sensible way? So that's the study. So if you're interested, you can provide the link to the study, the citations to the study. You can check them out. The next topic I've spent a lot of time on is sharing medical data with patient and families. So what we do is, how do we generate patient summary or treatment summary based on the EHR data? So we don't have to ask clinicians to write them again. And how do we actually also provide smart annotation so that we'll provide patients and family some contextual explanation. So I don't know if you have experience of logging into a patient portal or our kind of a personal health record system. You pull out your chart, but as an average person, as a non-medical person, you may have no idea about a lot of things going on in your medical document. So how do we use technology to provide contextual annotation, which all gives information about what is this medical concept, and so forth. And lastly, once you have that, how do we actually connect patients to online communities and peers? So if you have information about the patient, you also have information about other patients who are similar to this patient. Is there any way that you can actually build a community among the patient so that similar patients will be able to connect with each other? So what we did, so this work is inspired by this particular paper, which is how do we actually invite patients to read their doctor notes? And you will see that we have done a lot of work, a lot of foundational information science work, and also natural language processing. I try to determine what is the difference between a note, which is dictated, versus a note, which is typed into the computer system. And what are the features that we can use based on these two different types of documents to provide contextual annotation. And this is a prototype of the annotation software we're building. So this is a very common way doctors would write things. 65YO, that means years old. As a patient, you may not know what those kind of acronyms stand for unless you are very familiar with medical terminology and how people may quick write things. So the system is smart enough to automatically expand this kind of acronyms. And we also have, if we recognize this is a medical concept, such as a disease, then we are able to provide an article or online educational material about this particular disease. And then similarly, acronyms of a medical concept will provide contextual explanation. And we also, based on this information, we can profile the patient. There are some basic information characteristics of the patient. And we also have access to the same information of many other patients. And then we are able to cluster them and to identify who are similar to each other. And if they consent, then they are able to connect with other patients who are similar to them. They can talk about a lot of different things, such as how to live with the disease, and how much does treatment cost, and so forth. So the next piece of my research is information retrieval and text mining. So in this particular domain, I work on full text search engine for electronic health records, which is the system I'm going to show you today, and also contextual query recommendation. And I'll talk about what that is in a little bit. And then social information for aging. So the last piece is the main emphasis of this particular talk, collaborative search in electronic health records. All right, so with that, I'll dive into the main topic today. So this particular work was sponsored by the National Library of Medicine. The title is Developing an Intelligent and Socially Oriented Search Query Recommendation Service for Facilitating Information Retrieval from EHRs. And I want to acknowledge two collaborators of mine. I cannot do this work alone. I work with Dr. Qiao Mei from School of Information at the University of Michigan, as well as Dr. David Hanauer, Department of Pediatrics at the University of Michigan. And I'll talk about 4 different things about this particular study or this particular project or product. Motivation, architecture, and user experiment, which is how we evaluate the system based on the actual users using the system, and the implication of the research findings. If I have time, because before I came here, it was brought to my attention that this is something you may want to be doing at the UC Irvine. So I'll talk a little bit about the University of Michigan Health Informatics program. And I apologize if you are not particularly interested in this topic, but I see a lot of students in this room. So if you are considering entering a graduate program in medical informatics or health informatics, this may be something you may consider. And I'll talk a little bit about this program as well at the end of the talk. So motivation. In today's healthcare, we have a huge amount of data. It's much more than what we can handle. And 10 years ago, it was actually not the case. We have a paper, so we don't write a lot because we have to write. And now, because of the electronic system, we enter a lot of information, meaning that we copy-paste, we dictate, and we enter the information without thinking about who is going to be using the information and what kind of burden we're putting on those people by entering a lot of redundant, unnecessary information. So we are swamped by this type of information overload. And meantime, the data we're entering into an electronic system describing a patient are so bad in terms of, first of all, there are a lot of non-standard ways of writing things. There are a lot of different terminologies that are interchangeable, where people don't really have a consensus what to put in this document. So even as a human being, we read the medical chart. Sometimes we ask ourselves, what the hell is going on? So what does this mean? And if the quality of information is so poor, then it comes to this question, how do we actually use this type of data to drive medical decision making and to drive policy making in healthcare? So next is very poor organization of information. So this is a very typical design of a EHR system. This is actually used at the University of Michigan. So this is typically designed in a way that different types of documents of a patient, they are always arranged across different tabs. So you click on the first tab, it gives you some kind of document, and you click the other one, it gives you other types of documents. So they are separated by functional areas, lab versus radiology versus assessment plan, and so forth. So the logic, the relationship among the data are not being returned. So you have to think about lab report, the lab test, medication as distinct entities without relationship across them. And the other issue is also, so when we see the documents belonging to the same patient, the documents are always organized based on the time of their creation. So it's not organized based on some kind of inherent logic relationship, such as this particular medication is for this disease. And this group of documents were created because of this particular symptom or complaint of the patient. So the kind of a relationship among the documents or among the data are actually not there. As a doctor or nurse or pharmacist, when you see this EHR system, if you have in mind some information you are looking for, you have to click through each of the document in order to find what you're looking for. So that's a problem. And that's exactly the problem we are trying to solve. So now you see I lay out three things. And it has been a consensus among the medical informatics or health informatics community or the medical community in general that the increased availability of data does not, because of use of electronic health systems, does not automatically lead to increased availability of information. So we have a lot of data out there. We have no idea how to extract useful information from the data. So those are the three problems I laid out. Information overload in the digital age, and poor information quality of medical records, and lastly, poor information organization in a typical electronic health record system. So what is the solution to the problem? Before I move to our solution that we're trying to build, I have a brilliant teacher. So imagine you have a problem. Find out the email sent to you from Professor Gang. I'm sorry if I don't pronounce it. That contains the location of this talk. So if you have that task in mind, what would you do? What is the first instinct that you would do? Anybody? Yes?
I do know that the email program that we use for school, Gmail, there is a search bar at the top. So I would look up Professor Zheng, and then I would look at the lecture for the day, possibly your name, and hence it would likely come up with the email I have.
Precisely. search, by search. So you are not going to think about, oh, the email was from last week. So maybe narrow down to the emails from last week. And then try to sort them by the sender. And then try to look for all emails relevant and try to look for the location information, right? If you think about that, what you do is search. So let me just put in, University of Michigan will also use Gmail, by the way. So you just search UCI top public health location, and I just try not to prolong. Then you instantly get that email, and then you drill down to the email to find the location information, right? That's what we do things. And this is not what electronic health records are designed. In an EHR, you don't really have this kind of search functionality. You have to go, if you have something in mind, you have to go to the specific date, specific document in order to find the information. If you have no idea when that event occurred, you have to actually read through the document from top to bottom, the entire document of the patient. And hopefully, sometimes some of the information may carry over. So by reading the current note, you may be able to find the information that was documented initially many years ago or a couple of days ago, and then that's in your current document. Otherwise, you will never be able to find it unless you read through all of them. So search has become our instinct. Kind of everything you think about, what you're going to find out, either by in email or on the web, you put some information and try to search for it. So that is the new way of thinking about whether electronic health records could also be organized in a similar manner. So, find note of the patient describing a recent incident in which she suffered hearing loss from a car accident. Now, if you have that mindset, then you may challenging an EHR system, why can't I just enter hearing loss, and then I will find all documents of the patient that describe this incident. Okay? But it's not that simple. As I mentioned, the quality of information is actually very poor in EHRs. What about someone who did not really write hearing loss? What about hearing damage? What about other kind of ways that describe the same thing, but using different way of writing? Okay? Again, Google has provided a solution. So Google has this kind of contextual search in terms of if you search for Microsoft CEO, it knows who that person is. It even knows who that person was and give you the information. So this is kind of the contextual query expansion. You are searching for something, but Google is smart enough to know that there are some related concepts that may also be of interest to you, and will bring those things up. And also, what about something was spelled wrong? It could be in the document. It's actually not what was not entered properly in the first page. It could also be in the search query. And again, back to Google, they have some kind of solution to this. If you search for date mining, it's not a commonly used word. And know that you might be searching for data mining. And it will automatically recommend that alternative search term for you. So we have these kind of technologies out there. And the question is, how do we bring the technology of information retrieval to healthcare to facilitate finding information in medical records? So we have 3 problems. And I'm proposing this solution, which is first, how about search-based navigation in EHR? Instead of clicking each document, which is ranked by the creation date, so instead we actually search for the information that you may be interested in. And to do that, we have to have intelligent search term recommendation. Otherwise, as I mentioned previously, what if it's not spelled exactly as your search query? What if there was some spelling mistakes in the document? And also leveraging the collective wisdom of users. So a lot of people search for the same thing, right? As a medical doctor, or as a clinical or translational science researcher, you may be searching for the same thing, and then develop your own search expertise about this particular symptom, what are the words we should be using, about this particular patient characteristics, what are the keywords we use. How do we preserve that knowledge and share that knowledge to other people who are interested in doing the same type of research? So that is the last point, leveraging the connective wisdom of the users. And that's the collaborative search, which is not what I'm going to focus on. So there are a lot of unique challenges, as you have seen. I talk of retrieving information from electronic health records. So first is spelling errors. They could both in the documents you are searching for, as well as in the query that you enter. There are a lot of synonyms, interchangeable terms. They mean the same thing, but they are always, or they're often written in a different way. And how do we know those? Then how do we map them? Alternative spells and ambiguous aberration and acronyms. Those are all issues which are very challenging to solve in retrieving information from medical records. And last and most importantly, end users. They are physicians, nurses, and other type of supporting staff. It could also be researchers. They may be specialized in a particular subdomain of medicine, which means that they may not know everything about medicine. So they are typically unable to construct both effective as well as inclusive search queries. So we studied this problem extensively, and we have a paper about this issue. It's a query log analysis of the search engine. So we documented a lot of issues about user-constructed queries. So the key finding from the paper is that the quality of search terms entered by users was horrible. So what very bad. So meaning that just based on the user's own expertise of search, it's hard to believe that they will be able to get the information they want. So we want to provide some kind of technological help to support that process. So next, I'll talk about the system architecture of the search engine what we built for electronic health records. This diagram shows you the basic workflow of using such a search engine. So first, user initiate patient search. Sometimes it's not the entire patient records system, but a specific set of patients. For instance, if you are trying to screen patients for their eligibility for a clinical trial, you actually have a set of patients to start with. And then you construct search query. And next, based on the functionality of the system, the computer system might recommend you some alternative search terms or related terms based on artificial intelligence. Otherwise, you will retrieve the documents. The system will present results, and then you can either save that query as a bundle. So I'll explain that concept in a bit. You save the query as a connection of the terms, and then you can use that in the future, or you can share that to other people in the community. Or if you are using other people's bundle, a pre-stored connection of search terms, you can also read the quality of the shared bundle, and you can also modify the bundle and then recontribute that to the community. So that's the general workflow of the system. Now here is the user interface of the system. So it's very similar to Google in a way that you have a search box. where you enter the terms that you are looking for. So in this case, hearing loss, car accident. That's brain teaser 2. Very different from Google or any other kind of web-based search engines is that we have a query recommendation section where we put together a lot of alternative spellings of the same of the term you are searching for. So in this case, car accident, it can be written in a document as car crash, motor vehicle crash, or even acronymed as MVC. So there are so many ways that doctors may use to write that information. And the computers will be able to recommend almost inclusively every possible way that this information could be documented in the medical work chart. And similarly, we have hearing loss. We expand the hearing loss to many other related terms that this particular symptom could be potentially documented in the medical chart. So next, we present the documents, and by clicking into each document, you'll be able to see the actual physician note belonging to the patient. So this part is based on the contextual query recommendation function. And this part was built by a lot of different components. So first we have EHR documents. And we use MetaMap, which is a National Library of Medicine tool that parses medical concepts from a narrative free text document. And it's based on UMLS, which is a large connection of dictionaries in medical domain that contains different types of concepts that have been ever used in medicine. And we also have a query log, which based on the users, they enter a lot of terms, and we determine which terms are actually alternative spells of each other, and we put them into a dictionary. So over time, we can accumulate an empirical set of terms that people commonly use. And those terms are not necessarily in a formal medical dictionary. So based on that, we have a parsed documents. We have concepts extracted from the medical document. And then we use a free text search engine, NEMR, and index the documents. And similarly, for user-entered queries, we repeat the process, and we remove some of the generic semantic types, such as the patient, a person. Those are not very informative search terms. So now we have an expanded query, and apply that to the EHR document extracted, the concept extracted by the natural language process engine. We are able to then come up with a set of recommended queries. And that, we rank the documents based on their relevance. And then based on a lot of different algorithms, we are able to recommend highly relevant documents to users. Then we present the results. So we have a repetitive process to improve the performance of the system over time based on user input, as well as based on more and more documents being parsed and put into the repository. Okay, so that's how this part works. So now let's look at this collaborative search feature. So in the system, we have a bundle repository. As I just mentioned, a bundle is a collection of search terms that people enter into the system. And because the terms can be so complex, you don't really want to enter them every time. You want to save it into a bundle. And once you save that, you can then share the bundle to other people, either as a private bundle that only being seen by a designated list of users, or it can be a public bundle which can be seen by everyone. So now here, you can search, browse other people's bundle. So many of them are shared. And then once you have those, you can borrow them into your own bundle list, or you can build your own bundles. So that's the kind of the basis of the collaborative search concept. So once we have those saved terms, they carry or they convey knowledge about search and they become a media of disseminating search expertise across different users of the system. So next I'll talk about the user experiment. So how do we test the system with actual users, and what do they react to this type of search? We were not very optimistic at the beginning because we have no idea how medical professionals would be willing to share knowledge. First of all, share knowledge to other people, and second, they have egos. They have this kind of professional autonomy. They may not want to use other people's search terms. So we want to see whether that's the case. And again, so what I'm presenting today are all described in this particular paper you can find. So the user experiment went on for 4 years, and we tested the system with about 450 users. Majority of them are clinical researchers or translational researchers, or they are also practitioners with a research responsibility. And then we have also practicing physicians, coding staff, data analysts, and other type of QI, quality improvements people. So data are extracted from the system from the usage log. So essentially everything you do in the system, both search terms as well as other kind of activities, they are all logged. And then we perform social network analysis to see how people bond, how they are connected to each other in terms of sharing information and search expertise. In perfect setting, it's the University of Michigan Health System. And this is a network graph that we produced from the perfect data, and I'll go into more details. This is another network graph. We constructed 6 different networks. First is creator-consumer network. So essentially, this network shows who is sharing bundles to whom, and who is using others' bundle. We also constructed 3 different organizational networks, how different departments are sharing bundles, how different medical specialties, they are sharing bundles, and how different divisions, they are sharing bundles. And we also built a consumer network, which is a derived network. So in terms of this network contains nodes, which are users, and they are connected because they use the same bundle. So meaning that they are interested in search for the same thing. Okay, so that's the so-called consumer network. And we also constructed a hypothetical consumer network based on similar search terms entered ad hoc by users. So a lot of users, they actually enter the same search terms, but they are not leveraging the bundles. So meaning that those users could be potentially connected. Then they are able to reduce the redundancy of entering the same search terms over and over again, and also separately by different groups or by different people. So we use multiple network measures to determine the efficiency of the search knowledge dissemination across those networks. If you're not familiar, I'll just go through them very quickly. The first measure is a fraction of singletons. So essentially that measures the proportion of nodes which are not part of the network, meaning that they are not connected with any of the other nodes. Average degree, that means average number of nodes each node connects to. So if you are a network node, you are connected to 10 other nodes, so your degree is 10. Average tie strength, so each tie may carry a weight. So in this case, tie in our networks are primarily how many bundles are shared. If you share more, then the strength of the tie is higher. And the last one is average shortest passness. So just meaning that average number of hoops needed for a node to reach another. So if the network is very dense, it does not take you very much steps to reach another node. So the average minimum pass requires for a node to reach another. That's another measure that we use to measure the density of the network. So these are key network measures we use. So usage statistics. In the system, over a 4-year period of time, there are almost a million searches being recorded. Among them, about half were based on search term bundles. So those are search terms being pre-entered into the system, either by themselves or by someone else. And among these bundled search, there are about 36% used shared knowledge made available by other people. And about 26% of these, they are based on public bundles. And about 37% is based on private bundles. So just by reading this, you get a sense that this feature, this collaborative search feature, was actually heavily used by the users. So we originally thought that medical people, medical professionals, they may not be willing to share their knowledge, or they may not be willing to use knowledge contributed by other people. And this shows that this is not the case. So a lot of those bundles are used in search, and they are leveraging other people's search term entered into the system. They borrow each other's term. So these are top 10 most popular used bundles. If you're interested, you can height and weight, for instance, that's a very common bundle. And you cannot imagine how many different ways that people can enter into a system to describe the height and weight of the patient. There are so many ways. If you want to capture them, you actually have over 100 different terms in that particular bundle. Okay? So this is participation in collaborative search across different level of organizations, department, specialty, and division. The bottom line is there are lots of bundles being shared privately to other entities. So across different departments, there are actually a lot of sharing activities, which was pretty surprising to us. So we thought people mostly they work within a department. They don't really work with other people in other departments. And similarly, they don't across medical specialties, across divisions. So in fact, the data actually show that a lot of bundles are being shared across the boundaries of those organizational divisions. And also, a lot of bundles are being shared publicly. Anybody can use their bundle. They contribute the knowledge to the community at large. Okay? So this is a creator-consumer network. So what this means, I'll just point your attention to those few numbers. That's the percentage, the fraction of singletons. So essentially network nodes that are not connected to other people. So about half of the people, of the users, they are not connected with other people, meaning that they are not participating in network, in sharing or using of search term bundles. But which also means that there are about 42% of people that are actually participating. And similarly, you see that a lot of departments are participating, a lot of specialties, a lot of divisions that are participating in contributing bundles or in using search term bundles from other places. So let's get back to this network diagram. So what this shows you is that there are a significant amount of bundle sharing that links those clinical departments. So those clinical departments, they have a lot of bundles that they hold to themselves, they use internally. But there are some bundles that are being shared across different departments. So if we look into those bundles, you may see a lot of interesting stuff going on. So what kind of terms that people across different departments or different medical specialty, they share, they use in common. And what does that mean from both clinical point of view and from research point of view? So those are the type of information you can actually extract from learning the user behavior of bundle sharing across different specialty, department, division. And I showed you this earlier as well. this is the consumer network. The dots are users, and the edge is multiple users with 2 or more shared bundles in common. So meaning that if this dot and this dot is connected, those two persons, they used identical bundles at some point of time. And do they know each other? We don't know. They may not know each other, but they are searching for the same thing. So how do we use that information to promote collaboration in the community is our next question. So you see that in this network, there are lots of, in fact, disconnected users. And how do we bring them into the community so they can be participating in the sharing of search knowledge? That's also the next step. So based on the consumer network, we know that there are about 40% of 60% of users, they don't really share anything in common with other people. So they just search for their own thing. They have no common interest with other people. But which also means that 40% of people, searchers, they do have shared interests. And average degree, there are a lot of connected nodes. So if you are a person, on average, there are 9 other people who have searched the same thing as you did. And on average, there are those 9 people, they shared 3 bundles with me. So meaning that there are lots of interest in common. And the shortest path is 2.5, so meaning that for a person I don't know, that person's interest may be similar to me within just 2 or 3 people's distance. So if I know another person who is identical to me, and the other person linked to the other person, so it's actually a pretty dense network, meaning that people's interests are similar to a large degree. Right. So in a hypothetical, the network 6, the 6th network, based on similar queries manually entered by different users. So as mentioned that about 40% of users, they did not participate in sharing your bundles. They keep entering search terms into the system. And what we did is we extracted the terms that entered into the system, and we see how many other people also entered exactly the same term, maybe not in the same order. And we found that there are actually a lot of users that entered identical terms, maybe in a different order, but they are not saving that into a bundle, meaning that they cannot share that knowledge across people. If this knowledge were indeed shared, the fraction of singleton measure could reduce from 62% to 10%. So meaning that if everybody is using this feature, only 10% of users, they will be isolated nodes. They don't have any other people similar to them. So 90% of the people, they're actually similar in a way that they searched the same kind of terms. An average degree would increase from 10 to almost 50. So meaning that if we save our search terms, share to other people, on average, the potential could be there are 46 people similar to me, or there are actually 47 people similar to me that I can potentially connect to. So meaning that we can share bundles, we can share search terms, or in reality, in real world, if I don't know them, I may approach them. Why are you searching for this? What are you looking for? And how we can learn from each other, both for search as well as for conducting research, use the similar information. So this means that collaborative search has contributed to improve dissemination, but the potential was far from being fully realized. So then it comes to our researchers' question: how do we engage the community in more sharing activities? Implications. So we talked about the 3 major challenges of information, of the value of information in healthcare. One is information overload, and second is poor quality information, and third is a poor organization of information. And I proposed there could be a search-based navigation of electronic health records. And as you saw, it should have a very good potential if we build the system right. And to build the system right, the absolute crucial thing to have is intelligent search term recommendation. So again, medical professionals, they have no idea how this particular symptom may be described in the medical documents. And also, there are so many ways to describe the same thing. There's no possibility that a person would be able to inclusively include everything in their search term. So that's where the intelligent search term recommendation kicks in. And that's this particular section of the system I showed you. And lastly, we could leverage the connective wisdom of the users. So how do we make sure that medical professionals will save their query, make the query available to other people, so that can increase dissemination of search expertise across different users? So the implications, what we showed in the study, first, search social information for agent. I missed the A there. That is the so-called the term that used multiple people, they collaborate in order to find information, in order to construct information. And we were not sure at the beginning whether medical professionals would be willing to do this. And it actually shows that it works, even though the potential has not been fully realized. And if the collaborative search were not provided, as you see, up to 0.16 million searches that have to be manually entered into the system. And also we found that search term bundles are a crucial function. They serve a crucial function as a boundary object. So different people from different departments, from different medical specialties, they become known to each other through the shared search terms. And also those terms, they reflect similar shared interests in terms of both patient data as well as the actual work they are doing based on the data. Lastly, we also show that search term bundles, they represent a vehicle of organizational memory. So as you see that some of the terms are so complex, there are hundreds of individual terms in one single query. And that becomes a way to keep the organization, to preserve the valuable search knowledge. Otherwise, if people leave, then this search knowledge may no longer exist. So those are a few takeaway messages from this particular study. I'm doing on time. Not very good. 1 minute left. I'll just show you. I can actually show you this in a minute. This is our program. If you're interested, go to that URL. So what we do is it's a joint program between School of Information and School of Public Health. It's very unique. One of the first one of the kind. And it's a master's degree program, 2 years, a lot of coursework as well as internship. We also offer graduate certificate to many other people who are enrolled as a graduate student at the University of Michigan. First cohort, 2011, currently we have 42 students and 23 graduates. There are a couple of focuses of the program. And one is consumer-facing applications. We believe that consumers, the patients, families, informal caregivers, we believe that they are going to be the force that is going to revolutionize the healthcare industry. So we build applications for them. The second, design evaluation. This is something we are lacking right now in the healthcare industry. We build systems, we ship systems to clinicians. We have no idea how the systems are whether the systems are well designed and how the systems are being used. And population health management. So we manage the health at the population level instead of treating each individual patient. And we also focus on leadership in terms of how do we train the next generation of leaders in both health IT as well as in consumer applications. And if you're interested, we have a full loaded curriculum. I have about half of the courses offered from School of Public Health, half from School of Information. There are many also joint courses. So that's the talk today. So I covered motivation architecture, experiment and implication of this particular concept of collaborative research, and then Michigan's Health Informatics program. So with that, thank you very much for your time. If you have any questions, you can always email me. My email address is right there. Thank you.
Thank you. We do have time for 1 or 2 questions, and then, yes.
This is very, very informative, and it's focused upon, first of all, faculty, let's say, healthcare professional researchers who are trying to look for demographics about specific diseases and identify multiple patients that have those diseases, and thereby begin to do searches of this kind. And the value of that is obvious. You're also talking about building networks among patients, identifying patients who have specific diseases, and seeing if those patients can get together. I thought you were talking at one point about the patients themselves being allowed to do the search to find the other people. And this rings a bell in my mind about our institutional review board and their serious, serious concern about the protection of individual patient information. And how do these two concerns merge?
Absolutely, and not only institutional review board, but also the general HIPAA at large. They defined criteria and requirements for protecting security and confidentiality of patient data. So the answer to that is that's exactly what informatics can do, in a way that we are able to share patient information, but not disclosing the patient identity. So for instance, if as a patient, if you are searching for other patients similar to you, we were able to aggregate the data in a way that only when there is a significant large number of patients that it's not possible to individually identify them, then we are presenting the data. If the patient similar to you, there are only like 1 or 2 in the country, or 1 or 2 in your county or in your district, then we are not sharing that information to the patient. So there are actually a lot of informatics approach that I can use to prevent the confidentiality of patients, in the meantime, providing maximum information to the patient who is searching for the data. I think it's kind of we do have a solution. It's more of whether the institutional review board they buy into our solution or not. And I think it's always an issue because they don't understand what we do. And they just, to minimize risk, just don't share anything. And that's obviously not the way to do science.
Yeah, I understand, but their concern is critically important.
Absolutely.
We have to pay attention to their values.
Yeah.
Because their goal is to protect patients, protect healthcare professionals, protect the research projects we're doing and the treatments we're giving, protect our institution, protect the individual patient. So we have to work with the IRB. Yeah,
we work with them. We work with them. We educate them, and we bring them into the army of informatics. So instead of treating them as an enemy of us, we should really treat them as friends and try to get them into our group.
Yes, amen.
Are there enough places now that are able to accept the students in the master's program? They have to do 400 hours, and I don't know how widespread the electronic medical records is in agencies that might take them. Do you have difficulty placing students?
No, not at all. Actually, in the past 3 years, we have 100% placement rate. Because, first of all, they don't have to work with electronic health records. The health informatics is so broad, meaning that a lot of students, quite a few, they came back to California. They were, if they were from California, they came back to the Bay Area to work for startups. that are building applications for patients. Some of them, they went to Washington, D.C. to do house IT policy type of internship at think tanks, at consulting firms, and so forth. So it's actually, what we found in the past 3 years are all of our students are highly wanted, both as an intern as well as job candidates. Because in healthcare right now, there's so much need for high quality professionals who are not only understanding healthcare, but also technology. And right now, we actually don't have those people. We have a lot of people understanding technology. We have a lot of people understanding healthcare. We don't really have a lot of people understanding both. And this program is training people for that particular niche. And we found that it's very easy actually for us to place students for both intern and job.
Well, we can continue lunch over at ERB, but this is a little token from our students and faculty. Thank you again.
Thank you very much.
Sharing your wisdom with us. We appreciate it.